So just to set the context, if you go out there today and try to find out what is AI, how is it different from machine learning and deep learning, there's so many terms and so many things coming out at you. There's even marketing thrown in the mix, and it can be intimidating even for me with so many new technologies and papers coming out. It's very easy to get lost. So I'll just try to set some context about what is AI, what is machine learning, what is deep learning. AI is broadly the ability of a machine or a computer to do things that require some level of human intelligence. Machine learning is one type of technique that's driven by data. So given enough data, the machine learns what you're teaching it. And deep learning is a specific type of machine learning that learns through data, but it's inspired by how the human brain works. So there are several layers of neurons that talk to each other. That's how it's architected. And broadly, this is how you could draw like a Venn diagram of those. And AI has shown great results these days in computer vision, natural language processing, and speech recognition. There are some libraries you might have heard of, like PyTorch and TensorFlow and scikit-learn. They are some libraries that you integrate with. And deep learning is, there are some architectures, like convolutional neural networks are really good for computer vision. So ArcGIS already has several machine learning tools in the category of classification, clustering, and prediction. I'm not going to talk about it. This is more about integrating with AI. And the way you do that is you integrate with external frameworks and libraries. The frameworks could be web-based AI frameworks like Watson or Amazon's SageMaker. There could be libraries that you might have heard of, like scikit-learn, PyTorch, and TensorFlow. So to start off with, I'm going to give an example of machine learning, and then we'll focus more on deep learning. And one way to think about it is that with machine learning, you're typically dealing with tabular data. Deep learning can also do tabular data, but it's typically used with imagery, and it's showing great results there in the context of our discussion. So this is an example where we got a lot of data for accidents in Utah. And if we were to think about what are all the different factors, there's weather, there's temporal features like time of day, the month, or the seasonality. And there are spatial features like road width or the curvature, how far it is from an intersection, whether the sun is in the eye. And with so many variables, it can be really hard to make sense of like what's really causing it. And we need a machine to do this analysis for us. So this is just showing, when we get a problem like this, we try to find patterns. We do an exploratory data analysis. And these are some of the exploratory data analysis that we've done in Jupyter Notebook. So we see by all the accidents for the entire data set, by the day of the week, and the hour of each day. So you can see Saturday and Sunday there are fewer accidents, and each day there are these two peaks because of the morning and evening rush hour. And you start seeing patterns like these, and they tell you how there's also seasonality. So there are peaks and there are troughs. There's certainly something to do with snow is going on there. So this kind of an exploratory data analysis tells you what are the important factors or features that could be responsible for causing an accident. And once you know that, that's when you start pulling in all of those features into your machine learning model. So this is a data preparation notebook in which we've integrated with pandas, which is like a de facto Python library to work with tabular data, loading the data in it, and then it's about getting different types of data. So the different types of data, let me go to my slides to show you what all we had to consider. Yes. So we had to bring in a lot of data sets. We had to bring in where the crashes occurred, the average annual daily traffic, where the intersections are and which intersections have the traffic lights. We brought in weather from the weather stations, where the billboards are, the curvature of the road, and all of these are input features to our model. And once we built our model, and let's quickly look at the notebook where we defined the model and trained it and what insight we got out of it. The specific machine learning model that we used for this analysis was a gradient boosting model. And we were using XGBoost, that's a Python library. And we fit it to the data, and we start seeing some, one of the advantages of using a machine learning library, or in particular gradient boosting, is that it also tells you feature importance. So what are the things that were actually responsible for causing those accidents? So it turns out that the sun angles, solar azimuth, is an important factor in Utah. The temperature, so if it's the winter months, there's more tendency of crashes. So you also get these important features. And we were able to take that trained model and do a prediction on any given road segment. What's the probability of an accident happening? And those are visualized with the red road segments having higher probability of accidents, green having lesser, and we've overlaid the actual accidents at that time. So we are getting a good correlation between the predictions and where they really happened. So now I'm going to turn over into deep learning, and in particular, deep learning has shown great results with computer vision. These are some of the most important categories of problems in computer vision and how they relate to GIS. So on the left, we've got image classification, in which we take an entire image and we are trying to assign a label to that image. Is it an image of a cat or a dog? And for GIS, it could be used to take, images from a surveillance camera or some, monitoring someplace, assign a label to it. Then there's object detection, in which we are trying to find which objects are in an image and draw bounding boxes around it. And it's very important for GIS, trying to get insight out of imagery and putting it on a map. Then we've got semantic segmentation, in which case we are assigning a label to each pixel. So in this case, the yellow pixels belong to the cat class, and the green pixel belong to the ground, the blue belong to the sky. And in one geospatial application is land cover classification on satellite imagery. In this example, we are looking at roads from satellite imagery. And then there's instance segmentation, which can be thought of as a more precise object detection, in which not only are we creating bounding boxes around those images, but finding their precise boundary. This can be used to create building footprints and create better maps. So let's take a few examples of each, and we are going to look at the first example of where could you use classification and solve a problem. Okay, so here we are looking at SunTrust Park, which is a baseball stadium right outside of Atlanta, Georgia. And it is in a mixed-use development. There's markets, there's restaurants. So what's missing here, anyone? What's missing in this image? Parking, right? When a lot of people come, they need to park, and unfortunately there's no parking around this baseball stadium. What happens is that all these spectators, after a match, go and cross the first intersection. That's not a problem because there are these pedestrian bridges, but when they reach the second intersection, they go over a busy freeway, but there's a place before getting to the parking where they need to cross this road. And the police actually needs to stop that traffic and let the people walk through after a match, and they call it a scramble. So how did they solve this problem using image classification? So what they've done is that they've actually they are monitoring the pedestrian flow along these paths using cameras that are placed at these 3 locations that are looking at people coming out of the stadium, people at the first intersection, and those people coming to the second intersection. And those cameras are getting images like these. And what we've done is we worked with them to create an integration with IBM Watson, where we've trained their visual recognition system to take in one of these images, which is coming from that camera, and assign a label to it. So is it an image of a low or a medium or a high density crowd? And because we've trained that model, we get back a classification of a low density crowd. This one has a few people, so it gets classified correctly as a medium density crowd. Here's an example of what a high density crowd looks like. So all of this is used to build a dashboard that looks like this. And it's showing the time from 4 p.m. to 5 p.m. when the match was going on. And on the left, you see what the 3 cameras were seeing. So at the beginning of the hour, we see that all cameras are green. And looking at any image, we see there are not many people here. That's because they're all in the stadium. The match was going on, but that match ends around the middle of the hour, and people start coming out at that time. You're seeing the first camera is starting to see people coming out, and the other cameras are showing lesser activity. And that's when police can start to anticipate that people are coming out and they need to be prepared to initiate that scramble and manage the traffic lights. And that happens towards the end of the hour, where all of those people have crossed over from the stadium and they've assembled near the intersection. That's when they need to initiate that scramble. So what's the use of using AI in this example? The police actually uses it for several things. One is, from a central place, they can monitor the traffic and the pedestrian movement. They can manage it. Secondly, they can quantify the volume of pedestrian movement around a match like this and plan future events. And it also lets them see how well of a job they did. So in this case, we see that they did a great job at managing the pedestrians, because the time it took for them to cross over from that intersection is a lot less than the time it took for them to come out of the stadium. Another example of deep learning is for object detection. So let's look at that. So I'm going to move over to ArcGIS Pro, and looks like Pro just crashed on me. No, it's still there, sorry. Okay, so we are looking at residential parcels, and you can notice how some of them that have pools have been labeled, and the parcels highlighted in blue are supposed to have swimming pools according to the county record, but some parcels are with pools are missing in the data. So the data is outdated. We need to identify all the swimming pools and have them be assessed correctly. So ArcGIS Pro already includes tools that can help you label that data. So you can create, and label, mark some pools. I'm using the NAPE imagery to allow us to train a more accurate model, because the pools stand out in that. Pro also includes tools for exporting your training data. Once you do that, you arrive at image chips that you can use to train your model. Let's look at what that workflow looks like. So this is an example of using the new support that we've added to train a deep learning model for object detection using the ArcGIS Learn API in the ArcGIS Learn module in the Python API. And in about 5 or 6 lines of code, you can actually train your object detection model. So you just point it at the training chips that ArcGIS Pro extracted, and you load the data. It is telling me that there are 2 classes in it. There's background and there's swimming pools. Here I'm looking at those image chips. Then to train your model, you use a single shot detector, which is one of the faster object detection algorithms or models that are in use today. You find the optimum learning rate, and this tells me at which learning rate the loss is still going down, meaning that's a good learning rate to train your model. Finally, we fit the data to the model to the data, and you'll notice how with each epoch or pass over all images in my training samples, the loss is going down. Once you've trained your model, and this is an iterative process, when the loss stops going down, that's when you stop, and you can save an EMD that can be used in ArcGIS Pro for inferencing, or a deep learning package that can be used with image server. And finally, here we are looking at the results of that model, and you can see in just like 9 minutes of training with 10 epochs, my model is starting to learn where these pools are, even though it's not getting the location exactly right. That needs a little more training, but this is a way for you to judge how well the model is doing. Now we did one more thing with this, which was so these are all the pools that we found and the parcels that contain them for the city of Redlands. Another thing that we did was we also trained a model to, let's see, I need to load the neglected pools layer. So we trained a model to do classification on the kinds of pools. Some people maintain their pools and they're healthy, they're blue, but there are some pools which are not being maintained, particularly in foreclosed properties. So we also did a classification of clean versus green pools. And here we are looking at some of the pools that are infested with algae and could be breeding grounds for insects and mosquitoes, and how health officials can take this information and go visit them. So going back to my slides. Let's now look at doing object detection in videos. And we look at a video. This is a traffic roundabout in the city of Purmerend in the Netherlands. And I'm going to kick off a script here, this notebook, and let's see what it's doing. So here we are just looking at that video, and we are using a trained TensorFlow model. I'm running that in real time. That's taking the frames from this video, detecting the types of vehicles and pedestrians and counting them, and updating a feature layer in the background that's causing this dashboard to update, showing the volume of activity at that intersection at any given time. And behind the scenes, we have this notebook where we've integrated ArcGIS with TensorFlow to do this. So essentially, we load the trained TensorFlow model. Here, we load the layer that we'll be updating. And here's the code that's using TensorFlow to detect those objects and update the feature layer using ArcGIS API for Python. That's how we can run that. So it's interesting to do this real-time activity detection, but where it gets more interesting is if we can scale it up and do it for an entire city. And we actually did that for the city of Washington, D.C. We are looking at a dashboard for that, where we partnered with Traffic Land and their network of over 100 cameras. And over here, we are seeing in blue are those intersections where the predominant type of activity was cars, while in green are those areas where there are mostly pedestrians there. That I just clicked on a blue one again. but here it should be showing mostly pedestrians crossing the street. So that's how you can start getting a dashboard and managing traffic in a smart city. Now, this also allows us to start seeing interesting patterns. So what we observed was we recorded the activity for a particular day, and you're seeing how there's this random burst of activity in Washington, D.C. on that particular day. But right around 2 p.m., if you notice on this road here, the predominant type of activity is going to change from blue to mostly green. So it's telling us that there are a lot of pedestrians going there. So we were wondering if there's a protest going on or there are a lot of tourists. It was Memorial Day, and there was a parade going on at that day. So it can help us find these interesting insights. And where it gets really interesting is when you can start comparing the current volume of activity with historical trends. So this is a dashboard showing the activity thresholds for trucks compared to the previous recorded activity. So while we are still learning about, what the normal activity is at each intersection, having this kind of data will tell us if we suddenly notice a spike in the number of trucks or cars or a lower number of them at any given time. Okay, let's now look at few other examples. Let's move on to semantic segmentation, and I'll actually show you the example of finding roads. And I'm going to switch over to my slides here. So this is a Jupyter notebook, and one of the great things is that you can also turn them into slides. So this is a model that we've trained on two types of data. I've overlaid the road network on top of the satellite imagery. And you'll notice that the roads are not perfect. Some roads are missing, some are misaligned. But even with poor quality data, we can train a deep learning model to take in a satellite image and figure out which pixels belong to road. So this is a form of feature extraction, and here are some results that we are getting. So to take this further, we took a better model, and we were able to arrive at better results for an entire city. Let's see if we can look at those. So imagine if there's a new development for which you don't have the road networks. You could take a model like this and find all roads, or it gives you a good starting point to label all your roads using just deep learning. Now for good good maps, you need more than just roads. You need building footprints. So here is a model that's available on TensorFlow. It's called Mask RCNN. And this model allows us to find the footprints of a building. And here are some examples of that. And this is just a pre-trained TensorFlow model that I used. Now when we trained it further, using a lot more data, we start getting better results. So let's look at some of those. Here are the building footprints for Denver. And here are the building footprints for all of Los Angeles. So you can see how well this model is doing in finding these building footprints for both small and large buildings. Now, one of the problems with Mask RCNN is that it actually doesn't give you these regular building footprints, but really these blobs, which look more like Antonio Gaudi's buildings, masterpieces, than regular buildings with straight edges and right angles. But thankfully, ArcGIS has tools that can regularize these building footprints for you, and this is the results with that post-processing. So for good maps, you need roads, you need building footprints, right? Wrong. There's this incredible algorithm called CycleGAN that lets you go from Monet paintings to how they would look like as if they were photographs. You could go from summer landscapes to how they would look like in winter, or you could even turn horses into zebras given enough images of those. So let's see what it can do with maps. It actually uses a technique called generative adversarial network, in which there are two networks fighting each other out. There's a generator which is creating fake map tiles looking at the satellite imagery, and there's a discriminator that can tell good tiles from bad tiles. And when you train both of them together, they get better at their art, and they start creating good-looking map tiles. And it's mind-boggling what this network can do. So we trained it with satellite imagery and the street maps. Let's look at some results from that. And here it was able to go from this map tile, satellite image, to this rendered map tile without even having the road network or the building footprints or information on this was supposed to be a field or a park, that it's labeled correctly. We even did this for Stamen watercolor, which is a rendering style from Stamen design. And this network, like having seen a lot of those Stamen watercolor tiles, is able to go from satellite imagery to the rendered map tile in their design, even though we don't have their algorithm. So they are not going to be happy that we are doing this. Now it's starting to sound futuristic, but deep learning can already do things that you only saw in the movies. Here's an example of super resolution. So from this low resolution image, you can zoom in smartly using a super resolution network and tell that it's probably a woman walking. And then if you zoom in closely, she's probably carrying a gun in her bag. Just joking. So but then you can start reading text from these blurred imagery and start seeing what's there. So all that pixelation is gone. What I really like here is the way it handled the pixelated leaves of these trees. So now let's look at, we've got 2 minutes. Let's look at some creative AI. You might have seen an app called Prisma, in which you could take your selfie and take an artist style, and it rendered your selfie in that style. And a lot of people in deep learning, their GitHub profiles is as if some Van Gogh painted it. So let's do that to maps. Here I've taken an image of the Eye of Sahara. That's a geographical feature in North Africa, applied the style of this painting, and we are now able to generate map art in this style. Here's map art in another artist. Okay, that's the same one, but yeah, you could take another artist style and do it that way. So what's the practical application of that? One practical application is that this could actually be used for cartographic style transfer. So on the bottom right, we've got a Esri world street map view of Manhattan, a map of Manhattan. And I applied the style from the first world atlas from a cartographer named Ortelius in the top right. And we arrive at this map, that rendered map of Manhattan in the style of Ortelius, and it's even showing Manhattan as if it was a swamp, which it really was at the time. So with that, we've come to a conclusion of this. We only have 1 minute, so I just wanted to have this as a sort of inspirational talk to get you started and excited about what all deep learning can do for you. So thank you.